Hello, students. Today, we would like to continue discussing some of the models that we have with exponential and logarithmic functions. Last time we discussed financial models. Today, we would like to discuss two laws by Newton. Newton was, again, one of the greatest mathematicians and scientists who ever lived and is credited as one of the co-founders of the calculus, the other person, of course, being Leibniz. And so what we'd like to do today is discuss two models that Newton actually devised. I think you probably have discussed these possibly in science courses, or we'll discuss them later in your science and STEM courses as you continue in the STEM curriculum. So let me share my screen. Now, what's interesting about both of these is that, again, I'm going to move the page up a little bit and talk about the two different models that we have. As you continue to the calculus, you will actually learn the method to actually derive these solution curves. But what we want to do today is use the solution curves to solve problems because we have the understanding of the logarithmic and exponential functions, at least their algebraic qualities. And then, of course, when you take the calculus, you'll learn more refined attributes of these functions, and you'll actually learn how to solve these equations. Now, first, what we want to do is look at the growth and decay law. Sometimes this is called the law of uninhibited growth. Now, students often ask, how will we know which law to use? Well, it will be explicitly stated in the problem. This is not something that you have to figure out. It will be stated, and then you get to use that particular, solution curve to solve the problem. So in the first case, we have dE, which means differential equation, and we have the instantaneous rate of change of some quantity y that is time dependent is proportional to the amount of quantity that is present. Now, this is a law that Newton observed experimentally, and then he wrote the mathematics down and solved the equation using the calculus. Now, one thing that's interesting here is this equality we have here. What we're saying is initially at time zero, the quantity available can be expressed as y sub zero. That's just a notation, symbolic representation of the initial quantity. So in this case, the y of t is a quantity that is time dependent. And again, there are many quantities, maybe populations, a mass of some radioactive substance. Many quantities follow this law. And that's why it's so used in science. It's ubiquitous. It occurs throughout our universe, and it can be adjusted to mimic other conditions that may be required dependent upon the environment. So when you have this differential equation, the solution curve looks like something we've studied. That is, it's an exponential function. That is, the solution curve is y of t equals y sub zero times e to the kt. Now, k is a constant of proportionality, and that will be the case in both of these laws. So you can recall maybe in your algebra classes as having two quantities that are directly proportional, and you have a constant of proportionality, or you may have two quantities that are inversely proportional. These are similar ideas that use a constant of proportionality. Now, we're going to use this in the first couple of examples that I have, but I want to go ahead and apprise you of the second law that is very similar to the first. This is the cooling law, but an object doesn't necessarily have to cool. It can be heating, so to speak, but the name that is stuck is the Newton cooling law. Now here, again, like we had a time-dependent quantity, we have a temperature of an object that is time-dependent. And the differential equation looks similar to this. Note here that I am using the uppercase T for the temperature of the surrounding. And I'll say surroundings. And that could mean maybe the kitchen, the laboratory, outside somewhere. The surroundings would be the place where the object ends up, so to speak. You take an object that may be heated or cooled and you place it in the surroundings, and then the law takes over. For instance, in police investigations, forensics, you often want to determine the amount of time that a particular deceased person has been expired. That is, what was the approximate time of death? Now, even though that's fairly morbid and we don't like to think about these things, it's important to determine these particular parameters, especially when you're doing investigations. So the Newton law of cooling, just like the growth and decay law, is widely used. And you will find many uses for this as you continue your STEM education. But here we have the time-dependent rate of change, instantaneous rate of change of the object temperature is proportional to the difference in the object temperature and that of the surroundings. And what you find, again, when the initial temperature is represented as U sub 0, then the solution curve is not at all a surprise. That is, it is equal to the surrounding temperature plus this exponential term, which is multiplied by this constant, the initial temperature minus the temperature of the surroundings. Now, what you would expect is that as time progresses, this particular term will converge to 0. So if you actually place an object in a surrounding, some particular environment that has a constant temperature, as time passes, the temperature of the object will take on the temperature of the surroundings. Think about something that happens at home. If you take a dish out of a heated oven and place it on the counter, as several minutes pass, hours or whatever, the particular object will cool to that of the surrounding temperature. So this is something that is very intuitive to most of us, even more so than the growth and decay law, because we experience it daily. So again, we have the growth and decay and the Newton cooling law, which we want to use in some examples. So now let me move back up here to the first example from your lecture notes. The notes you have list some very good examples. And let me also emphasize, notice in this particular representation, we used y of t as the time-dependent quantity. It does not matter what letters you use. We often just use t for time, just for obvious reasons, and maybe we use an uppercase T for the temperature of the surroundings. But whatever letters we use to represent the object temperature and that of the quantity can be of our own choosing. So in this particular example, what we're going to do is utilize the uppercase N and just mimic the law of growth and decay is N of T equals the initial quantity times the exponential term. And sometimes instead of growth and decay, you will see the law of uninhibited growth. That's another phrase that is used to describe this law, and it's fine. Just remember, as I said before, you will always be told what law is applied to the particular situation. So you will not have to determine that. It will be part of the hypothesis of the question. So now in this particular case, we're given two initial conditions, so to speak. The initial condition about the quantity is here. That is N sub 0 is the quantity of N when time t equals 0, how it's represented here. And then if we're using t as hours, after 5 hours, the actual quantity is twice the initial amount. Okay, so what does that do for us? For instance, how does that change the actual equation for the quantity that's time dependent? Well, first we can say that when t is equal to 5, go up to our equation, replace t with 5, and then set the quantity equal 2 times the initial. We can actually solve here for e to the k. And let me show you what I'm doing. Notice the n sub zeros absorb. So these two quantities absorb, and then we're left with 2 equal to e to the k times 5. Now, one technique that I teach with these particular exercises is to change the base. Rarely do you need the value of k. What you need is e to the k. So instead of having to solve explicitly for k and go forward and backwards and forward and backwards, I usually just instruct my students to solve for e to the k. So basically what you have here is e to the k raised to the 5th power is 2. So raise each side of the equation to the 1/5 power to absorb the 5, and you have e to the k is just 2 to the 1/5. And now when you go back to the equation here, you simply replace e to the k with 2 to the 1/5, and then the law of exponents with the t gives you 2 raised to the t over 5. So now you have a very nice equation with a different base. Now, this is not required. However, what I find is that when students solve for k, they want to introduce decimals, and then that erodes the arithmetic properties of the actual solution curve. So you don't want to do any approximations while you're working with the solution curve until you have a final answer. And then you may approximate what you have. So you have one level of approximation that does not ruin the accuracy of your model. So just notice here, we will continue to solve for e to the k. So now we have a model that's very easy to use. That is, n of t is simply the initial amount times the exponential term 2 to the t over 5. So knowing the laws of exponents will be very helpful to us to make our equations nice and neat. Now, here's a problem that we're given from your lecture notes. Here, the specific initial amount of the quantity is 10,000. And again, this could mimic anything. Maybe this is just a population. For right now, it doesn't matter. And then if we go to our model that we have deduced, we can simply replace the n sub 0 with 2,000, and we have this. So we have a specific value for n sub 0. Now, here's the question. When the quantity is 25,000, what is the corresponding t? So we want to do a backwards problem. For instance, you might think of the forwards problem as substituting a value of t and getting the approximate size, the approximate quantity. Now what we want to do is go backwards. We think about the fact that the quantity is growing. And so we're thinking, let's go backwards. Let's figure out a possible quantity in the future and then understand how much time would have elapsed. So now we just work the problem backwards. So now we set the n of t in our equation equal to 25,000. Now notice we want to keep all of the calculations exact. As we execute the problem, keep everything exact. Notice the thousands here absorb. And we're just left with, in this case, if you go ahead and divide, 25 divided by 10 equals 2 raised to the t over 5. But of course, we can reduce this. We can reduce by 5s and absorb those. So we get 5 over 2 equals 2 raised to the t over 5 power. Now, at this point, you can think, well, I can use the power law and use any base I like. But since we have base 2, we can go ahead and just take base 2 logarithms. That is, what is a logarithm? It is a power of the base. So the power of 2 that equals, in this case, 5/2 is t over 5. So t over 5 is a logarithm. So by definition, t over 5 is the base 2 logarithm of 5/2. Now, you may have a client that is interested in a decimal approximation. And if you have a table of logarithms, or if you have a very supportable but simple scientific calculator, it may only have base 10 and base E logs. So now we can conveniently change to base E using the change of base formula. So this will just give us the natural log of 5/2 divided by the natural log of the old base, which is 2. So that's a real good way to review your change of base because it's very useful as we solve problems. And so now, when you look at this, we have an exact rendering of the actual time if we multiply by 5. So t is now 5 times the natural log of 5/2 divided by the natural log of 2, and this is exact. So what I recommend is using your knowledge of the exponential and logarithmic functions to get a nice clean answer. And now as you solve your homework, you can simply use your ln key to get an approximation. And what we find here to 2 decimals is that we get approximately 6.61 hours. And this number may be more helpful to your clients. Now, what's important here is that we've done exact calculation all through the problem to the very end. And then we introduce our approximation in a form that may be more helpful. So again, feel free to solve the problems as you feel comfortable. But notice by solving for e to the k, we simply end up changing the base, and we have a very neat, tidy equation that's easy to work with. Okay, let's look at another example. Now, the one I was talking about before, about forensics, this might be an example where we're trying to determine the age of an artifact. For instance, this is also important in investigation. If you are an archaeologist or anthropologist and you have discovered bones that you want to carbon date, this can be a very useful technique. Now, what we're finding here is you have a bone and it contains 45% of the original C14 content, carbon-14 being a radioactive substance that has a rather long half-life. Now, remember, the half-life is just simply the amount of time that it takes for half of the substance to decay. So half-life is very suggestive as to what it actually means. Now, why is this important in this particular case? Well, when the half-life is long, we're talking about thousands of years, then this makes an effective tool for dating particular artifacts. So what we have now, and what I've noticed here, and you may have noticed, is that I'm actually reducing the percent to a fraction, just like we did with the financial computations, making the calculations a little bit more neat, more tidy, so we can make approximations at the end. So notice here we have the 45 over 100. We factor the 5s they absorb, and we have 9 over 20. So the bone contains 9/20ths of the original amount. So what I'm using here is the same letters that we used in the first problem. Again, it does not matter. I mean, you know, when you think about it, any letter you like to use will be appropriate. So now we're thinking of the N of T as being the actual amount of the actual carbon-14, and that could be measured in milligrams or whatever measurement. That, of course, is unimportant to us because we have simply been given that we have 45% of the original content. Now we want to use the given information about the half-life. So, as I described, the half-life is the amount of time that is required for half of the radioactive substance to decay. So we see that we get 1/2 of the original amount of the carbon-14 equal to n sub 0 e to the k, where we replace the t in this case with 5,600. Now, what's interesting, just like before, the n sub zeros absorb. So we don't even really need to know what the original amount was. We simply need the information as to how much of it is left in the actual artifact. So now, if you like, you can write the 1/2 as 2 to the -1. And if you think about the last problem, we have the same situation, e to the k raised to a power. So now what we can do is raise each side of the equation to the 1/5600 power. So e to the k is now 2 to the power minus 1/5600. So now what we do, just like we had before, we can simply multiply the t and the power -1/5600 and get our growth and decay equation. That is, n of t is n sub 0 times the exponential term 2 to the power -t/5600. Now we can use our given information, our hypothesis, as to the amount of carbon-14 that is present. So we simply replace the n of t with that amount, 9/20ths of n sub 0. Again, just like before, the n sub 0s absorb, and we simply have 9/20 equal to 2 to the -t/5600. Now, just like before, we have a base of 2 since we have the half-life. Whatever the base is, you can just use that. And what's a logarithm? Power of the base. So -t/5600 is simply the base 2 logarithm of 9/20. So we see that these computations mimic really very closely the types of computations we did with the financial models. There's really no difference. And it's so good for us that we have this knowledge, because so many solutions to differential equations and so many models contain logarithms and exponential functions. So this opens the door to many other types of calculations for you. So now, of course, we're good to go. We can simply multiply each side by -1, and then, of course, divide by 5600. And here we have t is -5600 times the natural log of 9/20 divided by the natural log of 2. Now, of course, when we look at this, this is exact. This is an exact rendering of the time. Now, our client may need an approximation that they need to share with their company. And so if you use your natural log key, you will get approximately to actually a single digit year, 6,451 years. Now, again, this is not a precise time down to the second or the minute or even the day. This gives you a rough approximation as to how old the artifact is. And this can place the particular artifact in a certain point in time, which can be very critical for your investigation. So again, when we consider the use of half-life with the growth and decay law, we have a very, very useful tool for investigation purposes. So again, a very, very clean application. It's something you should study too. Share this with your friends as you learn these techniques, and just realize that you are only operating with your knowledge of logarithms and exponents. No new mathematics has been introduced here. We simply phrase the mathematics we know in terms of a different problem. Okay, so that was half-life. Now, let's look at an example that has to do with the cooling law. And then I have one example about a logistic equation. We won't have to look at the solution curve, but we just want to use our knowledge of exponents and logarithms to glean some information about it, okay? Now, the cooling law should remind you somewhat of the growth and decay law. One thing we do notice is if we just covered this term here, the laws would be essentially the same. We would have u of t equals some exponential term times a constant. But we have the additional term here. So it makes a little more computation, but very similar to the problems we've already been doing. Now, notice here, we have T measured in minutes, and we have the temperature of the object in degrees Celsius. Now, I'm not going to write the actual units with the numbers. We'll just simply know that these are the units that are being applied in this problem. It is often useful in a mathematical calculation to state them and then work through the problem. But if you would like to include the units, you certainly can. When I teach related rates in calculus, I usually use the units just because the students have so many varying variables. That's overdone, but so many variables to contend with and so many different rates. But feel free to include these if you like. I think it just makes the calculation a little bit easier to read if we omit them. Now, what we have in this particular case is that the initial temperature of the object is 90 degrees Celsius. The temperature of the surroundings is 25 degrees Celsius. So we're thinking we have to have just enough information so that we can actually use the particular solution as a predictor. I mean, we have to have enough information, so possibly we have the initial amount, or if we don't have the initial amount, we know how much of the quantity is available at some future time. We also know possibly another piece of information that will allow us to solve for e to the k. Again, as you work through these, we can look here and say that if we know this information, we should be able to solve for e to the k and get a complete predictor or a complete solution curve. Let's just see. Don't ever look at the problem and think, oh, I don't have enough information. Just work with it. And then if you have to go back and reread it to find some other piece of information, then that's the best way to go, because you don't want to stymie yourself and not move forward in the problem. Use what you've written down, work with that, and then go back to read the problem to see if there's some other information that you can use. So now we can simply substitute, in this case, the 25 for the surrounding temperature here, and then, of course, the initial temperature minus the surrounding temperature to give us the 90 minus 25, which gives us the 65 here. So when we look at this, we've got plenty of numbers filled in. So this is certainly an improvement, but we don't have the e to the k. Again, you can solve for k, but it's simpler just to solve for e to the k. So now we have this piece of information here. That is, after 10 minutes, the temperature of the object is 75 degrees Celsius. So now we can say 75 is the value for u of t when t is equal to 10. So we simply substitute those values here. And notice we subtract 25 and we get 50, and then we can divide by 65 to solve for e to the k raised to the 10 power. But just like before, we can factor the 5s from the 50 and the 65, and we're left with 10 over 13. So just by using the basic arithmetic, we have a nice clean equation. So 10 over 13 is equal to e to the k raised to the 10th power. Okay, so let's solve for e to the k by raising each side to the 1 over 10 power. Again, the 10's absorb, and we have e to the k equals 10 over 13 to the 1/10th power. But just like before, we'll just simply raise that to the t power and get the exponential term 10 over 13, which is our new base, raised to the t over 10 power. And then, of course, we've got the 65 and we've got the 25. So basically, when we solve, again, I know I sound like a broken record, but when we solve for e to the k, ladies and gentlemen, we get a new base. And don't worry if the base isn't your favorite base, like 2 or e or 10. Doesn't matter. A base is any positive number other than 1. Now, we're good to go. For instance, what do we want to use our model for? What do we want to predict? We're in the red box up here. We're doing the same problem we did before. I think learning how to do the backwards problem is the most useful at this point. It's easy to take a model and just substitute a number. That doesn't require a lot of knowledge. The knowledge is in producing the solution curve and then working it backwards. Now, what we're going to say is that when the object temperature is 50 degrees Celsius, what is the time that would have transpired? So we're going to do a backwards problem just like we did before, figuring out the age of the artifact. So at this point, we simply take this information and work it backwards. That is, we actually know the temperature 50, we know this quantity, but we don't know the T. So we want to solve for the T here. So in this particular case, we get some similar numbers. Notice 25 from 50 gives us 25. And again, we're dividing by 65 as we did up here. But notice the 5's absorb when we factor the 5's from the 25 and 65, and we're left with 5 over 13. Now again, what's a logarithm? Power of the base. Now I went ahead and kept the same base here just to make a point. If you just remember what the definition of logarithm is, you never misstep, and you practice changing the base, which is a good thing to know how to do, because when you take calculus, you will need to use that again. So we just do the base 10 over 13 log of 5 over 13 will now be T over 10. What's a logarithm? Power of the base. So the power of the base is a logarithm. And so now at this point, you can conveniently solve or change the base to the natural base. You're thinking you could take natural logs, you get the same answer. There's not a whole lot of extra step in what I'm doing, and what I'm doing actually helps you understand the process better. And so now, if we change to base E, we now have the what? The natural log of 5 over 13. And of course, we've multiplied by the 10 because the 10's in the denominator. And then we take the new log base of the O, the natural log of 10 over 13. So now what we see, just like with the last problem, we have an exact time. Now, of course, our client may need a number that's a little easier to share with their business. And if you use your natural log key, you will get approximately 36.4 minutes. So after these many minutes, 36.4 have transpired, then you would expect the temperature of the object to be 50. Again, the backwards problem is always the most useful, because we can make predictions. We can think about what we need to do in our experiments. We can think about what may have transpired in a particular situation. The growth and decay and the Newton law of cooling, very, very interesting. And what you'll find when you take the calculus, you will be able to actually derive these equations and come up with adjustments to these equations to mimic particular significant changes in surroundings that need to be accounted for to have a better model. So models can always be improved to reflect changes in the conditions. Okay, so the last example, it's fairly simple, but it just showcases a type of function that has an exponential term. Now, this is often described as logistic growth. And of course, as you continue in the calculus and you take, it may be a course in differential equations, or even in the calculus, this can be introduced. When I teach Calculus 1, I often do the solution of the logistic equation, because it's a nice application of logs and exponents and some really nice algebra. What you're going to find in the calculus is that there's an intense amount of arithmetic and algebra, which is basically why I teach the way I do, to get you ready for that type of manipulation. And you're finding that as you learn new ideas, you can magnify what you know about these ideas by adding more attributes as you learn more structure in the mathematics. So it is true that we continue to pretty much work on the same kinds of problems, We just add more detail to our analysis. Now, this is an interesting problem, and as we think about what we encounter as a society, and outbreaks of certain types of flus and viruses and things, this is always a very interesting type of model. Notice here, P of T will be the number of ill people T weeks after the initial outbreak in a city of 50,000. Okay, so this is kind of specific, and maybe this is a model that you have worked on for a particular experiment that you are doing. So notice here, the number of ill people is equal to this fraction, 50,000 divided by these interesting terms, 1 plus 60 times e to the negative 9t over 10. So this is an interesting problem from your lecture notes. So the first example, or part of the problem, was to determine what is the initial amount. I mean, how many people are sick when we start this process, when t is equal to 0. Now, what we're noticing here, and this is again t weeks, these are in weeks. So when we basically start the process, how many people are sick? Okay, well, we just replaced the t with 0. So now we just have what? 60 times 1 plus 1, so 50,000 divided by 61. And all I did here was just do some division. So when we divide, we get 819.6. Now, in problems in calculus, when you're looking for the number of subintervals to achieve a certain precision for an approximate integration, you always move up to the next integer value for subintervals. But here we don't really consider 6/10 of a person, so we truncate, as I've done here, written here, truncate the numbers. So we basically have 810 people who are initially ill. Okay. Now, the next question, and then I've done a little extra work here. So basically all this is utilizing your understanding of exponential functions to just simply, know what the predicting model says. So after 3 weeks, how many are ill? Okay, well, again, you might be surprised from this. We have 50,000, we have 1 plus 60e, and of course now we're replacing the t with 3, so we're going to get a negative 27 over 10. So now this is in the denominator, 1 plus 60 times e to the negative 27 over 10. So again, this is, like e to the negative 2.7. Okay, so when we look at this, we see there's a significant change. When we approximate this, we get 9,935 truncated. That is, now we have this many people ill. Now with this model, and what's interesting about this, and you're thinking, why is this number getting bigger? Well, I think you know. Well, this particular function here is a decreasing function. The power here is becoming more and more negative. And we understand that for this particular function being decreasing as t continues to get larger and larger, the function will get closer and closer to 0 in value. Okay, again, we think of the x-axis, in this case, y equals 0, as being the horizontal asymptote for the decreasing function. So we don't even have to think of the picture so much as just understanding that when we initially define the exponential function, when we have what we call a positive power, we have an increasing function. When we have a negative power, we have a decreasing function. So the coefficients are very important here. So now you can see, and I've just written this out, what would happen as t passes to infinity. So we're thinking lots of time has passed. What's going on with the number that are ill? Well, look at this. If we let t pass to infinity, the only part of the function that is actually, what do we want to say? affected, so to speak. Look at this. Notice the 50,000 has no T component. The 1 has no T component. The 60 has no T component. So the calculus allows us to move the limiting process to the parts that are affected by the T. So what we have done is we've just kind of bypassed the numerator and then moved the limiting process into the part of the denominator that has the T dependence. So I could say what parts of the formula are dependent upon T or impacted by the T. So now we look at this and say, oh, okay, well, now we're back to square one. We have the negative power. That is, as T gets larger and larger, the power of E gets more and more negative. So this particular term converges to 0 from above. Again, we think of the exponential function with the negative power as doing something like this. So as T continues to get larger and larger, the function values get closer and closer to 0. So now what we see is we basically have 50,000 divided by 1, which is 50,000. So eventually everybody gets sick for this particular model, which is kind of sad. But the idea here, again, as I've written, decreasing function. You can think of this many different ways. For instance, if you use your laws of exponents, what you see is that the base now is 1 over E, which is between 0 and 1. And that was our initial definition. The idea is that when you take more calculus, you will look at sequences. And when you have a base that is between 0 and 1, then as the power gets larger and larger, the function will actually converge to 0. And that's something that you can prove arithmetically with an epsilon and n type argument, which is similar to what you do with epsilons and deltas when you start the calculus. So what we see is that we can never avoid the basic premise of the calculus. And that's why we do the pre-calculus studies in college algebra and trigonometry, conic sections and sequences to prepare for the calculus. So again, this is just simply like, well, look at what we can do with our knowledge of exponential functions. Not difficult at all, no work to be done, except maybe just to realize that what we're having to do here is based upon the knowledge of the exponential function. So again, think of the problems we've done with finance and think of the problems that we've done with the cooling law and also the growth and decay law, and understand that we have plenty of understanding and realization of how things work just with what we've been able to put together in this class. So again, just remember, when you get to the calculus, we will provide a more succinct understanding of these functions that will allow us to create the full picture. But we need the preliminary information that we're learning now in order to make that less difficult. That is, the prerequisite material will undergird the work that you do in the calculus and make you much more confident. Well, I hope you've enjoyed the models that we have covered in these past 2 lectures. I think they're very interesting, and hopefully you'll enjoy studying them. We'll talk to you later. Thank you.